Dear students, greetings. Welcome to the course Advanced Materials Processing. In this course, we will be studying about review of mechanical behavior of materials, which we talk about plastic deformation, Griffith theory, types of fracture, that is brittle fracture and ductile fracture, type of failures like creep, fatigue, and finally selection of materials for the specific purposes. Now, not only this, we also study some of the basic engineering alloys like cast iron, steels, aluminum, magnesium, titanium, properties and applications of this material. We also study surface modification of this alloys, including surface treatment and coatings like thermal spraying, physical vapor deposition, chemical vapor deposition. We also study the properties, applications of non-metallic materials like ceramics, polymers, glasses. Finally, we will study the properties, applications of modern materials and alloys like nickel-based superalloys, shape memory alloys, high-strength low-alloyed steels, trip steels, smart materials, and metallic glasses. This course is the advanced version of the materials science which you studied in undergraduate. This will give you a complete overview of advanced materials processing. Before coming to strengthening mechanism, we will study something of plastic deformation or deformation permanently. We have studied in lower classes. The plastic deformation in materials is caused because of the phenomenon that is known as slip. Slip is nothing but sliding of the blocks of crystal over another along definite crystallographic planes that are known as slip planes. So in order to move the dislocations along the slip plane in the slip direction, you require a strength or stress which is known as critical resolved shear stress. So this critical resolved shear stress is much lesser compared to the theoretical cohesive strength of materials. So in order to cause a slip, we need to have a minimum stress level, that is CRSS. So in slip, atoms move an integral number of atomic distances along the slip plane. You just look at this. This is a dislocation. This dislocation moves along this slip plane and causes a slip of c few atomic distances. So the slip where it takes place, or the slip plane, is nothing but the plane which has the greatest atomic density, and the slip plane moves along a specific direction which is known as slip direction. So slip plane and slip direction put together is known as slip system. So we have for FCC, for BCC and HCP, we have specific slip systems along which the slip takes place. We can see here from this slide, in case of face-centered cubic like copper, aluminum, nickel, gold and silver, the slip plane is 111 and the slip direction is 11.0. We have 12 number of slip systems. For body-centered cubic materials like iron, tungsten, molybdenum, we have 12 number of slip systems in 110 direction, 12 number of slip systems in 211 slip plane, and 24 number of slip systems in 321 slip plane. In hexagonal closed packed structures, we have very less number of slip systems like 3, 3 and 6 on these specific directions. So we don't have so many number of slip systems in hexagonal closed packed structures. So the mechanism responsible for plastic deformation is twinning, and then twinning causes the slip to take place. So overall, if we just come to they speak of, the major mechanism that is responsible for plastic deformation is slip and assisted by twinning in case of BCC and HCP metals. As we have seen in previous slides, the strength of a material can be increased by stopping or delaying the onset of plastic deformation by slip. So these are the 7 strengthening mechanisms that are available. One is solid solution strengthening, and by reducing the grain size, that is known as grain size reduction. Then increasing the coal work, or increasing the percentage of the coal work, increases the dislocation or dislocation density, that is known as strain hardening. Then precipitation strengthening, dispersion strengthening, and fiber strengthening in composite, and Martensitic strengthening in steels. So these are the ways that are available to increase the strength. So these are known as strengthening mechanisms. So alloying or solid solution strengthening is one way to increase the strength of a material. So alloying is of 2 types. One is a substitutional solid solution, other one is interstitial solid solution. In case of a substitutional solid solution, we find that the for example, nickel and copper alloying, nickel atoms replace the position of lattice sites of copper atoms. That is, one atom substitute the lattice site of another atom, which is known as substitutional solid solution. In case of a interstitial solid solution, the smaller size of atoms like carbon, nitrogen, oxygen, they go and occupy the intersites or interstitial positions of the already existing parent element, so thus forming interstitial solid solution. So the forming of an alloy is based on the Hume-Rothery rules. There are 4 conditions that are there for Hume-Rothery rules, as we have known. Size difference factor, both the atomic size difference should be plus or minus 15%. Then same crystal structure it should have. Then valency factor and electronegativity factor. These 4 factors determine whether alloying can be formed or not. So this alloying is an effective way to increase the strength, because the impurity atoms that are added impose lattice strains on the surrounding atoms. This strain field interactions restrict the dislocation movement. So there are 2 types of strain fields. One is dilatational, or the strain field that are associated is equal in all the directions, that is known as dilatational, and some of the strain field are only shear type or directional, that is known as non-symmetrical strains. If you just look at it, the dilatational strains, they increase the strength up to 1/10 of shear modulus, whereas non-symmetrical strength, they increase the strength up to 3 times of the modulus. As we find that there are various mechanisms that are proposed to increase the strength by elastic interaction, modulus interaction, stacking fault interaction, valence interaction, short range order interaction, and long range order interaction. These are the mechanisms that play a major role in increasing the solid solution strengthening of metals. A few points that can be remembered in considering the mechanism that is associated with solid solution strengthening. Generally, substitutional impurities, they have spherical strain fields. Edge dislocations, they have both dilational and spherical stress fields. But screw dislocations, they behave differently. They have only shear strain fields. Coming to modulus interactions, differences between solute modulus and solvent modulus play a major role in increasing the solid solution strengthening. The effectiveness of modulus mismatch, or the effectiveness of solid solution strengthening, depends upon the size mismatch of the modulus mismatch between foreign atoms and parent atoms. Dissimilar valence of solvent and solute atoms also play a major role. The differences between both the valences of solvent and solute atoms. they have a role to play in solid solution strengthening. Apart from this, stacking fault energies, short range order, and anti-phase boundaries. For example, that is there in long range order has a role to play in solid solution strengthening. The other method to increase the strength of a material is to reduce the grain size in any material. Because we see that grain boundaries act as a barrier for dislocations. Because dislocations cannot penetrate through grain boundaries, because we see here the crystal planes are discontinuous at grain boundaries. In other words, like the misorientation between the grain boundaries increases, the yield strength also increases. So making a smaller grain sizes increases the misorientation of the grains, and therefore making a smaller grain size material increases the strength of a material, because we tend to have more obstacles than shorter mean slip distance. So we found that these grain boundaries are barriers to dislocation motion. So barrier strength also increases with the misorientation. So the Hall-Petch relationships give the yield stress dependence. So sigma naught gives the normal yield stress. Sigma I is a term denotes the friction stress or the overall resistance of a crystal lattice to dislocation moment. Then K is denoted as a locking parameter or relative hardening contribution to grain boundaries. Then D is a grain diameter. Thus we see the lesser the grain diameter, more the yield strength is. But this is not applicable to the grain diameter less than 4 nanometer, 5 nanometers. But so up to above that level, the grain reducing the grain size will increase the yield strength of a material. So we see the grain size dependence is on the flow stress at any plastic strain. Considering the mechanism that is responsible for increase in yield strength because of grain size reduction, we just look that at grain boundaries the dislocations pile up. The piling of dislocations causes the lot of stress concentration at the grain boundaries. When this stress concentration at the grain boundaries exceeds a value, they activate a new dislocation, because they become a source of grain boundary generation. Then the pileup is actually a source of dislocations that in neighboring grains. So then there is a very sharp yield point. This is a caution for a very sharp yield point increase of the materials. If you just take, there are two kinds of dislocations: statistically stored dislocations and geometrically stored dislocations. The geometrically stored dislocations are responsible for increase in strength of due to grain size reduction. So it is based on the fact that dislocations will experience hindrances while trying to move from a grain into next because of abrupt change in orientation of planes. That's what we have seen. So the hindrances can be of two types. One is forcible change of slip direction, because slip direction changes, and discontinuous slip planes. Both direction factor and the plane factor has the role to play in the hindrance. So conclusively, the smaller the grain size, then the dislocation hindrance is more. So the smaller the grain size, we can see the yield strength of the material will be increased. When the material is deformed plastically below the recrystallization temperature, that is known as cold working. So a cold worked metal becomes stronger and harder. That is known as strain hardening. The strain hardening increases the strength, but from that temperature, if you increase the temperature, it lowers the rate of strain hardening, because that is known as hard working. So generally the materials are strain hardened at low temperature, so that's why we call it cold working hardening or work hardening. So during plastic deformation, the dislocation density increases. And normally an annealed metal will have 10 raised to the power 2, 10 raised to the power 6 per square millimeter number of dislocations, whereas the cold work metal will have 10 raised to the power 10 number of dislocations per square millimeter. You can just compare the measure how much the number of dislocations that will be there in a cold work metal. Not only that, the increased number of dislocations, because of which the interaction with each other, that's what increases the yield stress. So we can just look at it how the increase in dislocation density is. So this is a typical grain boundary. Even 10% of cold work steel, this is a typical diagram of that, we'll have high dislocation density along the grain boundary. They form a cellular substructure known as tangles. They increase in stored energy. Not only that, generally a cold worked material is deformed in such a way that we always get elongated grains into preferred orientation. So as we have seen, there are a large number of dislocations that are there in a cold work metal. So thorough interactions of stress fields of the dislocations increases the strength of a metal. They produce sessile locks. Not only that, they form a dislocation jogs, as we have seen in the animation, where the one dislocation which has to move along the slip plane has to interact with so many number of dislocations that cut through the slip plane, that there will be lots of formation of dislocation jogs which would consume a lot of energy. Then the strength of a material is increased. Typically in a cold worked metal, people as research said, 50,000 or more kilometers of dislocations are there in cubic centimeter if we arrange the dislocations lengthwise. So many number of dislocations are being generated or formed, of which through their interactions the strength of a material is increased through the cold work. Coming to dispersion hardening mechanism, the oxides, carbides, nitrates and borides, which are smaller in atomic size, are added with the matrix and they are mixed thoroughly. Then this alloy is produced through powder metallurgy techniques, in which we find this oxide particles or carbide, nitrate, boride particles are dispersed throughout the ductile matrix. So this dispersed particles, though they are arranged not with coherency, but they give more resistance to recrystallization and grain growth. Then when the dislocations pass through, they cut through the zones if the stress reaches a high value. But generally the dislocations move around the particles, they form a loop and they bypass them, because of which we get a very high strength due to the dispersion hardening. We also see here from the picture, this is how the dislocations move through the particle. They sometimes, if the stress reaches beyond the value, they cut through it and it cuts the particles. But whereas like oxide dispersion strengthened alloys or ODS steels, they have a very high creep resistance. In fact, high temperature strength is increased because of this dispersion hardening. So the next mechanism is precipitation hardening. As we see here, this is a phase diagram of element A and B. Let's look into 3 temperature. T0, T2 and T1. At these three different temperatures, we find the composition of B in A is different. For example, at here, we find, say for example, if it is 18%, here it is 10%, here it is 5%. But we find that generally with allowing increases the strengthening. So what we do, we heat generally the material to a higher temperatures, increase the solubility of B in A, suddenly we quench it to this temperature so that we can retain the composition of B in A, B in alpha as it is in high temperature. That means we have the higher solubility retained even at the low temperature by heating it to a certain temperature and quenching it. So we can have the higher solubility which will cause increase in strength. So this is known as precipitation hardening. So copper beryllium alloys or aluminum alloys, these all are treated with precipitation hardening. They have a coherency. That means like you have equal number of distribution of atoms of aluminum alloys as well. Element A and element B for certain zones. Those all are known as GP zones or Gumer-Preston zones. The dislocation interaction between GP zones and the dislocations, are quite similar to that of dispersion hardening. If you just look at here, this is known as Orowan mechanism. So these are the GP zones or dispersion hardened materials. When a dislocation passes through, they bow or bend before the dispersed particles. They bound more, they leave a loop and they pass through the particles. What happens? This loop, when some other dislocations pass through, they have to exert more energy, more strength to pass through this. So the strength of a material increases. This is known as Orowan mechanism. So we get the increased strength due to the precipitation hardening. At the same time, increased percentage of alloying. The other mechanism that is involved here is fiber strengthening, which is generally used in composites. We know the composites are the materials which has a high strength to weight ratio. We had fine fibers in ductile matrix. These fibers, they have high strength, they have high elastic modulus, and they don't react with the matrix. Generally viscous alumina, boron, graphite, tungsten metal wires, glass fiber reinforced polymers. These are the examples of fibers, and like in concrete, the steel rod takes the load, and like that here in composites, fibers take the load whereas matrix pass on the load. The tensile force is for the whole composite is calculated on the basis of rule of mixtures, where AF and AM are equivalent to area of fiber and area of matrix respectively. And the composite forces having calculated A and F and smaller A and F, modulus and strain and area. In this calculating for the rule of mixtures, we have an assumption that both fiber and matrix strain equally. So we have the strength of the ductile material increased through the addition of fibers. In steels, we do a transformation that is known as Martensitic Transformation, where we quench the austenite and we get martensite. The transformation is a diffusionless transformation from body face-centered cubic to body-centered tetragonal. Martensite is body-centered tetragonal structures. But during quenching, the during the formation of martensite, they have a lot of parallel twins and high dislocation density is produced during quenching. Then this carbon atoms strain the ferrite lattice. Then there is strong binding is set up between dislocations and the carbon atoms. So the presence of martensite increases the strength of the material. We can find it from this diagram. With increase in carbon percentage, this is this periodic carbonate structure. This is the hardness. This is the paralytic structure hardness. We look at here, because of this typical dislocation and structure and twin structures, we find the hardness of martensite increases tremendously with increase in carbon percentage. Your patient for hearing, I have used Guider by Mechanical Metallurgy, then Courtney by Mechanical Properties of Materials, and used this YouTube video for a recording of for animation.